Hello everyone. The most well-known feature of quantum mechanics is that it is weird. But why should it be that way? The experimental data in quantum mechanics does not have contradictions. The equations of quantum mechanics are very straightforward and precise. They also do not contradict each other. Only when we try to interpret quantum phenomena, something strange takes place. So we have to ask, does nature contradict itself? Or is this a case of human error? The goal of this presentation is to show you that quantum mechanics can be interpreted as a self-consistent theory. It only appears to be strange because of conceptual confusion. In fact, quantum phenomena lose their mystery if we avoid mixing up wave properties with particle properties. I want to show you that even the most difficult puzzle in quantum mechanics, which is the EPR paradox, can be solved in this way. Let us begin with the most basic facts. Elementary physical entities have a dual nature. Waves have particle properties and particles have wave properties. It seems very hard to say where the waves end and where the particles begin. However, it is not impossible because the two aspects become manifest in different ways. For example, light is made out of photons. What do we know about the photons? They always propagate like particles. If we try to detect them in open space, or if we try to detect them inside interferometers, they always behave like discrete entities. It is impossible to detect a single photon in two places or more at the same time. So, if we always detect them like particles, then let us assume they are particles. On the other hand, single quanta contain very little useful information. In order to understand their physical properties and how they are expressed in any given context, we need to detect them in very large numbers. When we do that, we see a remarkable thing. The distribution of quanta in any plane of detection is wave-like. By the way, it often sounds confusing that quanta have wave properties when they can only generate discrete events. The explanation is that we are talking about the information revealed by the position of each event. At any point of detection, the quantum wave function has a predictable profile. For example, an ideal wave with sharp momentum has to converge on a single point in the focal plane of a lens. As you can see, all the rays are bent after they pass through the lens. They have different directions. However, all of them were parallel before they hit the lens. Hence, a quantum detected at this point corresponds to a wave function profile with sharp momentum at the source. All the geometrical components are parallel and come from a large surface of emission. In contrast, the geometrical components of the wave function in the image plane correspond to a very small point of emission. Hence, all the quanta detected at this point reflect a virtual wave component with a single source point of radiation. The spectrum of position is now sharp, but the spectrum of momentum is wide. To sum up, quanta arrive like particles, but they reveal information about complementary wave profiles. I wish to insist, in both cases we are dealing with properties at the source, and both of them are wave properties. Many teachers describe the position profile as a particle property, but this is a mistake. It takes a very wide lens to get a sharp position profile, and this only makes sense in a wave model. In other words, the real quantum dualism is not between waves and particles, but rather between different types of wave-like profiles. Quanta always arrive in discrete lumps, and their distributions are always predicted by the wave function. This tells us that quanta do not propagate independently like bowling balls. Instead, their propagation takes place under the influence of some kind of wave process. Of course, this is a remarkable observation, but is it irreducibly weird? Is there no analog for such behavior in nature? Consider, for example, a surfing venue on a perfect day. A large number of surfers are crowded in a small region on the ocean surface. The waves propagate towards the shore and carry surfers with them. The thing to keep in mind is that different waves can overlap with each other. When the waves interfere constructively, we expect a large wave to emerge. Therefore, many surfers will try to catch it. When the waves interfere destructively, there will be no wave to speak of, and no propagating surfers on it. Accordingly, the distribution of propagating surfers is determined by the net amplitude of passing waves. If we had a long surfboard counter stretching parallel to the shore, we would not be able to detect the waves. Instead, we would detect a large distribution of discrete events in a wave-like pattern. In particular, we should expect many discrete agents in the areas with constructive interference, and very few in the areas with destructive interference. As you can see, there is nothing strange for a distribution of discrete events to carry information about wave properties. Of course, the quanta are not really surfing on boards. We still know very little about the nature of their guiding waves and how they interact with each other. Still, the point remains. Quantum mechanics is not weird because quanta have wave-like distributions. Our stories about quanta become strange when we try to use wave concepts for the description of particles or particle concepts for the description of waves. For example, we use words like superposition, interference, and spectrum when we talk about waves. We use words like collision, trajectory, and uncertainty for the description of particles. If we apply any of these concepts to the wrong category, confusion becomes unavoidable. Let us consider a particle surfing a wave. We know it is coming towards the detectors, but we are perfectly ignorant about the actual outcome. It may arrive here, or here, or here. For this reason, we can say that the location of the next detection event is uncertain. Keep in mind, this is a classical phenomenon. We know that the wave profile determines the probability distribution, but once that is taken into account, everything is straightforward. We never know where the next quantum will strike, but we can assign a precise probability to each available point of detection. This, of course, is not weird because we are using a particle concept to describe an instance of particle behavior. Still, this is only one aspect of the so-called quantum uncertainty. Let us now focus on a single point of detection and ask ourselves, how is the probability of detection determined at this location? As a rule, we need to take the net state of the wave function at the point of interest and square the amplitude. But how is that net state calculated? Suddenly, we are dealing with a wave process. In order to calculate the net amplitude of a wave at a fixed point, we need to add up all the component amplitude vectors. Again, the probability of detection is higher where the net wave is taller. Yet this outcome depends on a large number of components. Even with coherent waves, some amplitude vectors point up, others point down, and there are intermediate angles as well, depending on the plane of polarization. A single particle surfing such a wave must respond to all the inputs at the same time. It sounds as if the particle should be in one of several possible states and we should have uncertainty, but this is not the case. Let us consider the nature of classical waves for a minute in order to bring more clarity to this concept. What is a wave? It is a propagating disturbance. Elastic media transfer momentum from one region to the next, creating a well-known pattern. Note: individual molecules are perturbed but do not travel. Instead, the state of motion is transferred from one carrier to the next. Unlike traveling objects, these states of motion can become superposed. For example, if two molecules act on a single molecule, it carries forward their total effect. In other words, two types of action merge into one. What happens during superposition? There are two aspects to this. Quantitatively, we have many vectors that add up. Physically, we can only have one net state. Look, if any of these two players kicks the ball, it can go in one direction or the other. If both players kick it at the same time, the ball must go in the net direction. It cannot go in two directions at the same time. In the same manner, wave components vanish when they become superposed, and only the net states are physically observable or consequential. Here is a simple demonstration. If two pieces of rope are connected, we can produce several oscillations at the same time. This is a vertical wave, and this is a horizontal wave. When both types of action are applied simultaneously, the rope cannot move in two directions at the same time. Only the net wave is physically possible, and it propagates in the diagonal plane. In short, elastic media can respond to many types of motion at the same time, but they are only able to move in the direction of the net state. On paper, it looks like many components go through each other. In real life, there is only one net state, which is equal to the vector sum of all the components at every point. For this reason, a surfing entity can only be influenced by the net state of a wave. For example, imagine a particle surfing a double-slit interference pattern. The probability of detecting the particle in the areas with perfect destructive interference is 0. The only way to obtain this outcome is if both components are active at the same time. It is not possible to say that the particle is in only one component state or the other. Consequently, it is not correct to even suggest that we have uncertainty about which component is real. Instead, we have certainty that all the components are acting at the same time. Again, it is not the particle that is in many virtual states at the same time. It is the wave. To be precise, the wave has only one real state, which is equal to the sum of many virtual components. In other words, the net state of the wave can have a complex structure, in which case it has a wide spectrum. To be fair, it is possible to translate wave superposition into particle uncertainty. For example, we can pass a visible electromagnetic wave through a prism. The input projection has a wide spectrum which is broken down in the prism. If we have a single photon in this projection, it can end up in only one output channel. In this case, we have uncertainty. The photon can end up here, or here, or here, but never in two places at the same time. Still, this is an example of classical uncertainty because it refers to our ignorance about the state of the photon after passing through the prism. More importantly, the broken down spectrum is a completely different physical state. When all the components are superposed and overlap onto a single point of observation, they disappear into the net state. They may exist here in a physical sense, but not here. There is only one wave function at the input, but three wave functions at the output. I wish to emphasize, this is a fundamental property of quantum mechanics. The quantum wave function is typically formulated in phase space because only the net state vector is physically relevant. The wave function determines the profile of particle distribution, which means that quanta can only express the total profile. Indeed, the statistics of quantum detection events is not separable into wave function components. This is the essence of quantum interference. Therefore, the proportion of detected quanta always expresses the net state of the wave function in which all the components produce effects at the same time. That is why the concept of quantum uncertainty does not work. We can either have classical uncertainty when we discuss particle properties, or classical certainty when we discuss wave components in superposition. This confusion between particle concepts and wave concepts is particularly damaging when it comes to non-commuting quantum variables. First, what does it mean when two variables do not commute? In physics, different properties of the same object are typically defined independently from each other. So any operation on one of them has no effect on the other. As a result, the order of operations on the same object does not matter. Yet, some variables are defined together, such that one cannot be separated from the other. One example of such a relationship is the canonical conjugation, in which two variables are Fourier transforms of each other. In plain English, we have two complex properties. Each of them has its own spectral structure. Yet the product of their spectra is constant. As a result, one of them has to have a wide spectrum if the other is sharp. Such relationships are not possible in the case of classical particles, but they are practically mandatory in the case of waves. The main difference between waves and particles is that the waves are complex entities. They always express collective effects. That is why we expect wide spectra for many variables. For example, consider the profile of a collimated beam. The geometrical structure of this projection is captured by a set of parallel arrows. Notice, there are many arrows, but they all point in the same direction. Therefore, the spectrum of momentum at the source is sharp. It can only contain one value. On the other hand, we know that parallel lines cannot intersect. Therefore, every arrow requires its own starting point. This means that the spectrum of starting position is maximally wide. What happens if we switch to a divergent beam? Suddenly, radiation can flow in every possible direction. In this case, all the non-identical arrows start from the same point and cannot possibly be parallel. Therefore, the spectrum of position is sharp, but the spectrum of momentum has to be wide. As you can see, it is impossible for the spectra of these two variables to be sharp at the same time. Here is a simple way to visualize such transitions. When a multimode beam passes through a lens, it will evolve by going through many different profiles. In the focal plane of the lens, the laws of optics predict a sharp momentum spectrum at each point, and a correspondingly wide position spectrum. In the image plane of the source, the opposite happens. The wave profile is now sharp in its position spectrum, but the momentum spectrum is maximally wide. Now you might ask, how is it possible for the same wave to behave as if it was emitted like this, and then to switch as if it was emitted like this? The answer is very simple. These are virtual profiles. The wave function does not really evolve like this. Remember, we are dealing with a multimode projection and only the net state is real. It just so happens that the wave function at this particular point is mathematically equivalent to a beam component with this structure. At this other point, it is mathematically equivalent to the conjugate profile. And so, a particle that happens to surf the pilot wave at these points will behave as if it has the same properties. If we detect many particles at this point, they will produce a distribution that expresses a collimated beam profile with wide position spectrum. In contrast, the particles that get to this point, regardless of their actual trajectories, will add up to a distribution that represents a divergent beam profile with wide momentum spectrum. As shown above, quantum variables are not particle properties. They are wave properties expressed in the distribution of large numbers of particles. By the way, this process is easy to understand because we use the word spectrum to study wave properties. But what is the name of this process in quantum mechanics? It is Heisenberg's uncertainty principle. You see, the name of this concept makes us imagine strange things about quanta. It forces us to apply particle properties to wave phenomena. If we give up the image of a wave with quantifiable spectral structure and replace it with the notion of particle uncertainty, things become very confusing very fast. The question is, do we want to perpetuate this mistake? If not, then the solution is to change the name. With this in mind, we can now tackle the problem of quantum collapse. How are detection events predicted in quantum mechanics? Quite simply, we calculate the state of the wave function in the plane of interest and use that profile to determine the probability of detecting individual quanta. The first question to be answered in this context is how do we get discrete events out of a continuous wave function? This is an important problem, but not a difficult one. In a pilot wave model, this is a natural consequence. Waves are continuous, while the particles that surf them arrive one by one. If we cannot see the waves, but we can see the particles, then we have discrete events. You see, if we do not confuse waves with particles, there is no mystery and no collapse to explain. Still, the story does not end here. The concept of collapse can also have a different meaning. The standard mechanism in classical wave propagation requires the constant superposition of multiple components. Consider the Huygens Fresnel principle. This molecule pushes on all the adjacent molecules, creating a wavelet. Then, every molecule from the wavelet pushes on its own neighbors. It is unavoidable that many wavelets will act on a single point at the same time. Therefore, the wavefront evolves through a process of constant superposition of multiple components. We can have different phases, different frequencies, different polarizations, and so on. Yes, there is only one net state, but it has to be complex with a rich spectrum. In the same way, the quantum wave function also has a wide spectrum for every property. You may recall that unmeasured quanta are supposed to be in many states at the same time. If so, how is it possible for quantum measurements to reveal sharp properties? Isn't this a process of collapse? The first step in this demonstration is to remember that superposition means interference. When multiple wave components overlap, it is possible for them to cancel out completely at specific locations. Note, we start with many input components, but we end up with zero. In the same manner, it is possible for all but one component to cancel out, in which case we get a sharp spectrum. Thus, we can get exact states via destructive interference. The second mechanism for this outcome is constructive interference. Let us go back to the example of waves on a rope. If the two input waves are in phase, then we get a linear state in the diagonal plane. This net state is physically indistinguishable from a wave that is created by shaking the rope directly in this plane. Hence, the two components vanish and are replaced by a sharp net state. In short, it is possible for multiple components to overlap and to produce a net state with sharp spectrum if the details of their interference are appropriate for that. The lesson to be learned here is that the spectrum of the net state is not identical to the list of input waves. There is an infinite number of ways to produce a net state, yet the spectral structure is the same in every case. And so it is perfectly natural for a wavefront to start with a fixed number of components and then to evolve through various kinds of net states. In this case, an optical beam can pass through regions in which the momentum spectrum is sharp, while the position spectrum is not. Later on, it evolves to a state with opposite structure. In conclusion, the number of input components is independent from the spectral structure of the net state. Any variable can evolve to have a sharp spectrum sooner or later. Nothing ever needs to collapse. Here is the best part. If quanta do not collapse, then they do not need to know how they are measured. Look, the wave function predicts a sharp momentum spectrum here. This means that quanta are going to have such a property in this plane and only in this plane. At the same time, a sharp position spectrum can be observed only here. It is not the quanta that collapse. It is the wave function that evolves. Therefore, we need to place the detector here for a sharp observation of momentum. If not, we have to move it here for a sharp observation of position. More importantly, the measurements do not verify sharp properties exclusively. Non-commuting variables are inseparable from each other. So, the same measurement that reveals a sharp momentum spectrum also reveals a wide position spectrum. Remember, there is no uncertainty here. There is only certainty that all the spectral components are present at the same time. Therefore, measurements do not create quantum properties by magic. They simply expose them as they happen to exist objectively and as predicted by the wave function. In other words, it is not the quanta that know how they are going to be measured. It is the people that know where to place their detectors in order to observe desired properties. Finally, we are ready to discuss the nature of entanglement. Suppose that we make two beams such that every quantum in one beam is identical to another quantum in the partner beam. If so, then both beams have identical wavefronts down to the microscopic level. For this reason, two identical surfers will experience identical interactions and will follow identical trajectories. As you can see in this drawing, we have two particles that arrived at identical points in the focal plane of their lens. Therefore, they will behave as if they belong to identical virtual profiles. The quantum source has many modes in superposition, but the wave function spectrum at this point looks as if it belongs to a collimated projection. In short, both quanta will express the same sharp momentum state, and both of them will express a wide position spectrum at the same time. If we do not detect the quanta in the focal plane, they must continue to propagate until they reach the image plane. Again, they will surf the waves in identical ways and arrive at corresponding points in this new plane of detection. This time, they will behave as if they have a sharp position spectrum and necessarily a wide momentum spectrum. The key element is that quanta have transient properties. They do not preserve their properties from the source. They start with identical properties and then experience identical steps of interference. At each point of detection, they can only express the net state of the field as captured by the wave function. The question is, how much can we learn about one quantum by measuring its twin? Keep in mind that particles express wave properties, but the wave profile changes at every step. If we measure one quantum in the focal plane, then we know for sure the properties of the other quantum, but only when it is in the same plane. If we measure the second quantum in the image plane, we can predict the properties of the first quantum, but only if it happens to arrive undisturbed at the same destination. If we detect one quantum in the focal plane and the other in the image plane, their properties are independent from each other. And so, it can never be the case that we can describe the particles with sharp momentum and sharp position at the same time. Remember, we are not discussing instantaneous particle properties. We are describing virtual components of wave spectra at the point of detection. This is the only kind of information that we can extract from quantum distributions, and this is the only kind of information that quantum mechanics can predict. Consequently, it is possible to describe the behavior of entangled quanta without any kind of contradiction or paradox. This should not be surprising because we eliminated the concept of quantum uncertainty from the start. When we are dealing with wave spectra, we acknowledge the equal reality of simple and complex states. There is no motivation to look for hidden properties in the case of wide spectra. More importantly, there is no contradiction between the described behavior and the fundamental principles of quantum mechanics. And if there is no paradox, then there is no need to invoke strange elements, such as non-locality, in order to fix the interpretation. By now, I suspect that many of you are wondering, what about Bell's theorem? I have shown you that pilot wave models can explain quantum behavior without complications. Yet the current consensus in quantum physics is very clear on this issue. Pilot wave models should be avoided. Why? Because they are believed to obey Bell's inequality. So let me tell you, this is a very unfortunate mistake. In actuality, pilot wave models violate Bell's inequality with necessity and naturally conform to the predictions of quantum mechanics. This conclusion might sound surprising to many viewers. That is why I want to explain it in greater detail. To begin, let us consider a few historical details. Bell's theorem was published in 1964. It showed that hidden variable theories, which violate Heisenberg's principle, are not compatible with the formalism of quantum mechanics. However, Bell did not show why quantum mechanics violates his inequality. He only proved that it does. Many years later, in 1980, Therelson improved on Bell's theorem and showed that quantum correlations obey a different limit. Today we call this limit Therelson's bound. In other words, there is something about hidden variable theories that makes them obey Bell's inequality. And there is something about quantum mechanics that makes it obey Therelson's inequality. But what is this mysterious something? The answer to this puzzle was only revealed in recent years through a series of unrelated papers. Here is a short list of publications that I found to be particularly instructive. As you can see, around the year 2010, it became sufficiently clear that the culprit is commutativity. In short, hidden variable theories have to obey Bell's inequality because they rely on models with properties that always commute behind the veil of appearances. Quantum mechanics belongs to a class of models in which some properties do not commute in a fundamental sense. Hence, Bell's inequality was declared a test of non-locality at a time in history when its actual physical meaning was not fully understood. So what do we know now that wasn't clear in 1964? Suppose that we have to analyze the properties of a large stockpile of laundry. We need to take into account two properties, color and texture. We can ask, what is the correlation between these two properties? Given that one piece of clothing is white, what is the probability that it is made of cotton? In order to answer this question, we need to run special tests and figure out the rate of coincidence between specific colors and specific types of fabric. It is a remarkable mathematical property of such tests that they have to obey some constraints. One such constraint is Bell's inequality. Please note, the reason that Bell's inequality applies is that every property is discrete and sharp. A shirt is either white or red or blue, but never in several states at the same time. The fabric is either cotton or wool or synthetic, but it is always fixed to a single value. This property is the determining factor for the upper limit of Bell's inequality. In contrast, when we have wave qualities, we have a different class of variables. Specifically, wave properties can have wide spectra because we are dealing with group effects. We are no longer constrained by the rule to have only sharp properties, and therefore Bell's inequality can be violated. However, wave spectra are not arbitrarily wide. In special cases, we have non-commuting properties which are canonical conjugates of each other. I have said this many times already. When a wave has a wide position spectrum, it has to have a sharp momentum spectrum, and vice versa. What happens to the coefficients of correlation if we impose this restriction? No surprise here, they have to obey Tyrrell-Son's inequality. To sum up, Bell's inequality is only able to eliminate the particle-based models in which all the variables commute. It is simply irrelevant for the classical wave models in which many properties do not commute. Therefore, any classical pilot wave model of quantum phenomena is immune from Bell-type analysis. The simple explanation is that quantum correlations obey Tyrrell-Son's bound because they are wave properties. In retrospect, this should not be surprising, because quantum phenomena are predicted by wave functions, not by particle dynamics. Here is another way to think about Bell's theorem given these new conclusions. The Copenhagen Interpretation insists that quanta have either particle aspects or wave aspects, but never both at the same time. Yet, entangled quanta allow us to reveal the presence of wave properties even when we measure the so-called particle aspects. Quantum correlations are always wave-like. Therefore, Bell's inequality confirms the formalism of quantum mechanics and falsifies the Copenhagen interpretation. It tells us that the interpretation is not compatible with the formalism. That is why it has so many paradoxes. So, how did the Copenhagen interpretation get it so wrong? The simple answer is that wave concepts were confused with particle concepts. For example, when two beams intersect, the virtual structure of the waves can be captured with straight rays. If we forget this is a macroscopic profile, it is tempting to think that the rays are particle trajectories. Indeed, the Copenhagen interpretation insists that we can obtain path knowledge if we place our detectors here. Yet in a real wave, the energy cannot go through. As shown above, only the net state can be real. Hence, the Copenhagen interpretation created a story without physical basis, in which quanta are assumed to carry unchanging properties, like billiard balls, straight from the source. Keep in mind, it would be impossible to claim this distribution contains path knowledge if such a particle picture was not taken for granted. On the other hand, if we place our detectors in the interference volume, we see fringe distributions. Again, these virtual arrows are confused with particle trajectories, and now we are supposed to imagine a completely different reality. The quanta still roll from the source like billiard balls, but this time they carry so-called interference knowledge. By the way, the existence of interference fringes and separated beams is not a problem in classical wave theory. This net state is able to evolve into that net state as a matter of course, as predicted by the Huygens-Fresnel method. Yet, Copenhagen gets into contradictions because of the insistence that component rays are particle trajectories. As it is well known, Niels Bohr even dismissed this problem on the grounds that the two measurements are mutually exclusive. From his point of view, no empirical paradox was possible. Of course, Einstein, Podolsky, and Rosen explain that the paradox still remains, because the two states can be revealed at the same time with entangled quanta. If particle properties are carried unchanged from the source, then we get two contradictory realities for the same particle. This measurement reveals one reality indirectly. This measurement reveals another reality directly. Taken together, they lead to a contradiction with the formalism of quantum mechanics because non-commutativity is lost. The only way to make the story stick is to invoke more mysteries, such as spooky action at a distance. To sum up, this whole debate about paradoxes, hidden variables, and non-locality is an internal problem of the Copenhagen interpretation. If we do not confuse wave concepts with particle concepts, then we can follow the spirit of the quantum formalism directly. Quanta reflect the net state of the wave function objectively and change their properties at every step. At the end, I wish to emphasize, the equations and the experiments of quantum mechanics are very successful. This presentation is not intended to question their validity in any way. Unfortunately, the interpretation of quantum phenomena is a completely different story. For decades, we have been trying to understand basic physics with strange concepts that cannot be justified. Uncertainty, collapse, measurement-induced reality, non-locality. These are all examples of confusion between the properties of waves and particles. The same process of confusion led to the illusion that pilot wave models do not work, when in fact they are the best candidates. The Copenhagen interpretation is in direct contradiction with itself and the content of the quantum formalism. If we switch to a pilot wave interpretation, then we can achieve a paradox-free understanding of microscopic physics.